lecture number is this?
15 if you're not counting the sub.
Call it 16. Lecture 16. Okay. So let's do a computation. So compute using the definition. Okay? So if you recall, the definition is that's the definition of the definite integral, right? Where the limit is taken over all possible partitions of the interval AB. Now, if delta xk is equal to b minus a over n, so if we take equal subintervals, then the integral from a to b of f of x dx turns into the limit as n goes to infinity of and then we can just write delta x because all the delta xk's are the same. Right? And we said that this taking equal subintervals makes the computations easier. So for this example, f of x is x. Okay? And I can choose any point in the in each of the subintervals as my ck. So I'm going to choose the right endpoint for each subinterval. So this is the kth subinterval. I'll use the right endpoint for each subinterval. Right? So having said that, the integral from a to b of x dx is the limit as n goes to infinity, the sum from k equals 1 to n, and f of ck is just ck, because f of x is just x, so that's just xk, right? And delta x is delta x. And let's figure out what xk is. Well, if this is a, and that represents x sub 0, right? If xk is somewhere here, then that's the same as saying a plus how many subintervals are we going to go to the kth subinterval? K times delta x, right? Yeah. Okay, so x sub k is just a plus k times delta x, which is b minus a over n. So let's write that down. So x sub k is a plus k times b minus a over n times delta x is b minus a over n. Alright? Now, this quantity, as far as the sum is concerned, is fixed. It's constant. It doesn't change with k. So I can factor it out of the sum. And then I'll have the sum. And so we could use some of the rules for sums, right? So we could break this up into two sums. And again, as far as the sum is concerned, this is a constant. So we factor that out. And we'll have the sum of k. Okay? Did What is the sum of a from k equals 1 to n? A-n. What's the sum of k? Very good. Okay. So in here we can quickly simplify these two, right? And then if I were to multiply out by b over a, b minus a over n, I would get b minus a times a, the ends would cancel here. And then for this one I would get plus b minus a squared over 2 times n plus 1 over n. Right? B minus a times b minus a is b minus a squared. You have a denominator of 2. And then you have a denominator of n times n plus 1. Okay? Alright, so as n goes to infinity, this is fixed, right? So let's just expand this. That would be ba minus a squared. This part over here. And for this part over here, we can expand this so we get plus b squared over 2. The middle term would be minus 2ab over 2, so it would just be minus ab, ba. And then the last term would be a squared over 2. Now, as you can see, ba and minus ba cancel. And so you get b squared over 2 minus negative a squared plus a squared over 2 is minus a squared over 2. And so that's the answer. Okay? Okay, and this is shown in the notes. Please keep this calculation. Alright, so let's summarize what we just got. So, in summary, the integral from a to b of x dx equals b squared over 2 minus a squared over 2. And this is a very useful formula because we don't have to do this again. If I have the integral from 0 to 1 of x dx, then according to this formula, it's just 1 squared over 2 minus 0 squared over 2. So it's just 1/2. Right? So I can integrate this way. So it's a pretty useful formula, but more important than the utility of this formula is trying to find a connection between the original function and the answer. Okay? Now, let's define a new function. Okay, let's define capital F of x to be x squared over 2. Okay, and the motivation to define f of x as x squared over 2 is as these expressions over here. Right? Alright, so and we're also going to define as before our original function that we were integrating, that f of x was x. And it's not very hard to see what we get over here. The relationship between big F and small f is quite apparent. Do you notice what it is? How is big F related to little f? Okay, the derivative of big F is little f. Right? Okay, and that's pretty important. Okay, this indicates that there is a relationship between integrals and derivatives. Yeah? And later on, we're going to write a theorem that tells us exactly what that relationship is, and that's going to be the fundamental theorem of calculus. Okay, it kind of gives us a bridge between differential calculus and integral calculus. Okay, and that's a pretty important result, because how did we start differential calculus? We started it by talking about the tangent line problem, right? Or the velocity problem, or the rate of change problem. And the way we started integration was we started talking about the area problem. Okay? So in one sense, we're trying to find the equation of the line tangent to a curve, and that calculation gave us the derivative. And in the other one, we're trying to find the area under a curve, and that gave us the integral. And these are seemingly unrelated problems, geometrically at least, right? But it turns out there is some evidence here that these two ideas are related. And that's the point of the lecture today, is to see how deep that relationship is, and what we can learn from it, and how we can use it. One of the most useful things about that relationship is that we don't have to do integrals with the definition anymore. We'll have a quick way of doing them. Okay? We won't have to go through the definition of the integral as the sum of the limit of the Riemann sum. So anyway, let's see what we have here. So if I write it this way, okay, then I notice that the integral from a to b x dx could be written as big F of b minus big F of a. Right? If f bf is defined as x squared over 2, then f of b is b squared over 2, and f of a is a squared over 2. So we could just write it this way. Okay? Do you notice that? Okay. And so one statement you can make about big F and small f is that the derivative of big F is little f. Yes? But there's an opposite way of looking at that. That big F is the antiderivative, okay, of little f. So in other words, we know that two different functions can have the same derivative, right? For example, what function has a derivative of 2x? X squared, right? But what is another function that has a derivative of 2x? X squared plus 1, right? So there are so many functions that have the same derivative. So how do we pick the correct one? Right? So what this big F was a function whose derivative is x, right? But that's not the only function. What if we pick a different function whose derivative is x? Will it still work? So there are many functions such that there are many functions, capital F, whose derivative is f. Not only this one, but many more. As a matter of fact, any function that looks like this with different c's will produce the same derivative. Okay? So this expression represents all such functions. Okay. Now the question is, will the formula still work? This formula, I guess, where big F is any function whose derivative is x, okay, even if it's not that one, what if it's this more general? Will this formula still hold? Well, let's see. So if I do f of b minus f of a, then f of b with this f is x squared over 2 plus c, right? Minus f of a, sorry, this is b squared over 2. F of a is a squared over 2 plus c. Okay, and what does that turn out to be? B squared over 2 minus a squared. The c's cancel, right? So that's good, because we don't have to guess the correct function among all of them whose derivative is x. Any of them would work, right? Any of them would work. So if that's the case, then I'll pick the simplest one. I'll pick the one where the constant is 0 from now on, because any of them will work, at least for this function. So the question is this a coincidence, or will this always work? So in other words, so if I were to pick my guess is this is going to be f of b minus f of a, where f is a function whose derivative is 3x squared, right? What function has a derivative of 3x squared?
X cubed.
X cubed. Okay, x cubed plus c represents all of them, but let's try this one, okay? So in other words, I'm guessing, again, this is still a guess, we don't know, that the integral from a to b of 3x squared dx is b cubed minus a cubed, according to this. Okay. So that type of computation allows me to make this guess. If this is true, it really simplifies the way we do derivatives. Yeah? Versus that whole mess of computation that we had to do. So what we're going to spend some time doing is verifying that yes, this always works. We're always allowed to do this under certain conditions. And okay, that's the fundamental theorem. So let's take a look at this. Let's take a look at this theorem. Oh, and there's a whole other. Let's come back here for a second and look at this. What's happening here from a to b, there are many values from a to b. For example, the definition requires us to cut up a to b into small pieces, take an x in each of those pieces, and then evaluate the function, multiply by the length of the subinterval, and then add the whole thing, right? And then take the limit. So the definition is asking us to use the whole interval in a sense, right? Do you see what I'm talking about? You cut up the interval, take points in each subinterval, and then do the computation. But another thing that's really fascinating about this is that the answer to this integral only depends on the endpoints of the interval. You don't have to worry about the numbers in there, and that's a big deal. You see what I mean? And in higher dimensions, in 2-3 dimensions, in calculus 3, you'll see that there's a theorem like this, okay, that only depends on the endpoints or the boundary of this region. So that's a very powerful theorem for that reason. Okay, an integral's value depends only on the endpoints. Okay, and picking the right function. Okay, so that's what I want you to take with you when you read this next theorem. So here we go. Fundamental theorem has two parts, and this represents the first part of the fundamental theorem of calculus. So it says, suppose f is continuous on closed interval AB. Okay? then the integral from a to b is capital F of b minus capital F of b. And the relationship between big F and small f is that the derivative of big F is small f. Okay? And this is the part of the theorem that brings the derivative into the picture and relates it to the integral. All right? So let's do an example here. Let's integrate from 0 to pi a function 2 cosine x dx. Okay? I should probably give you the notation here. That's simpler to write. Another way of saying this is to say f of b minus f of a is written like this, f of x ab. Okay? This just means this. It's a shorter way of writing this. Alright? So we have to come up with a function whose derivative is 2 cosine x. But forget the 2 for a second. The derivative of what function is cosine x? Sine x, okay? And of course, constant multiple rule tells us the derivative of 2 sine x is 2 cosine x, right? So I want to evaluate 2 sine x from a to b, right? Or well, actually from 0 to pi. Okay, what that means is I just want to evaluate this function at pi, all right, minus at 0. And sine pi is 0, and sine 0 is 0, so this is 0. That's the integral. Okay? So here's another example. Okay, try to think of what the Riemann sum would look like with cosine as your function. Right? It wouldn't be very pretty. So here's another example. Well, it's actually verifying this. So integral from 1 to 3 of 3x squared dx. The integral from 1 to 3 of 3x squared dx. Again, so you want to think of a function whose derivative is 3x squared. Of course, that's x cubed. You want to evaluate that from 1 to 3. So that would be 3 cubed minus 1 cubed. 27 minus 1 is 26. Okay? So integrals just got easier. Right? All right. So let's put that on hold for a second and think of a special function. So let's take a function that's continuous on AB and not negative on AB. And let's define another function, g of x. Or I should say, yeah, I'll call it capital F of x. And I'll define it like this. The integral from a to x of little f cubed dt. Okay? And we're going to define this for x being between a and b. Let's draw a picture to see what this does. So we want to draw a function that's not negative between a and b. So maybe this function here. Here's b. question is, what does this function give us? Okay, in terms of area, okay, the integral from a to x of f dt is basically the area of under this curve from a to whatever x is, right? So if this is what x is, then f of x is just this area. Does that make sense? And as we move x further right, the area gets larger, right? Okay, so what's happening is capital F of x is, you can think of this as an area function or an area accumulation function. Because as x changes, area accumulates if x goes from left to right. Okay? Does that make sense? All right. Now, the argument I'm about to make works even if f is not, f doesn't satisfy this condition. So f can be positive or negative. But the picture looks nicer when f is only restricted to be positive. But the mathematics works. And what we're going to do is we're going to see that if I change x by a little bit, how much does capital F change? If I just change x by a little bit. Okay? Of course, a little more area accumulates, but how much more area? Yes? And that's what I'd like to study now. Okay. We'll try to draw the same picture now. Okay, so we're gonna say that x changes just a little bit. So it goes from x to x plus h. So h is small. All right. And we want to see how much f changes. So we'd like to. What does this represent from the picture? This is the area from A to x plus h, okay. And I want to see the change in f, so I have to see what f is here minus what f is here. How much big f changes? Right? All right. So, okay, so let me see what happens here. So this is equal to, using the definition of capital F, this is basically the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. Right? Does that make sense? Okie dokie. So, using some of the properties of integrals for one specific property, we could rewrite this. And how do we rewrite this? Well, I could rewrite this and say, okay, this is the integral from a to x, right, of f of t dt, plus the integral from x to x plus h of f of t dt. That's just this part, right? So to go from a to x plus h, I go from a to x and then x to x plus h, minus the integral from a to x of f of t dt. And then something cancels here, right? The first, these two cancel. Okay, that's great. So let me summarize what we have so far. So what we have so far is that f of x plus h minus f of here we're going to use the fact that little f is continuous very, very carefully. Okay? So, we're trying to integrate f over this small region, x to x plus h, yes? So let's think about what happens in that interval. If h is really small, right, then f of x and f of x plus h are really, really close together. Does that make sense? Okay, so that's the whole point of continuity. That if I change x by a little bit, the function doesn't change by much, right? So what that means is, if h is small, f of x plus h, right, is almost equal to f of x, right? Is that true? So as h approaches 0, f of x plus h approaches f of x. That's the whole point, right? Okay. So how could we verify that? So let's see over here. If I were to think of this in terms of its Riemann sum, what I'd like to do is I'd like to cut up this subinterval, or this interval, into really small pieces, right? But the point is, and I'll do this informally. I'll do this very informally. As h approaches 0, right? As h approaches 0, then pretty much f of x is constant. Because in a really small interval, if the function is continuous, then it doesn't change much. So you could pretend like it's kind of constant, right? So if I were to say that it's constant, then the integral from x to x plus h of f of x dt, and this is a constant because the variable is t here, okay? What is that equal to? In other words, if I have a constant function from x to x plus h, right? Here's a constant function, yes? What's the area here?
fx times h.
fx times h, right? So this is, so going back here, I could say that right? Approximately. Yes? And if I divide by h on both sides, this is approximately f of x. Yes? Does that make sense? No? But this looks like something interesting, yes? Especially that h is small. Okay, so let's write this. Okay, so we're doing all this informally, but in the limit as h approaches 0, this part is the derivative of capital F. Right? Okay. Remember what capital F was. What was capital F? No. No. The definition of capital F in this example was the integral from a to x of small f of t dt. Right? And on this, that's f, but I want to write f prime, right? So I want to write the derivative of this. So the derivative of this. Yes? So is equal to little f of x. Right? Does that make sense? It's just a different notation here. I could very easily write this as d by dx of f. The derivative of f is little f. Okay. To make all this argument more formal, won't take much more work. Okay, pretty much very similar to this. So what have we said? If you were to read this, you'd say the derivative of an integral is the original function. So in a sense, the derivative and the integral are kind of opposite operations, right? They kind of cancel each other out, so to speak. And you're just left with the function. Yes? All right. So part one of the fundamental theorem told us that there is a relationship between the two. There's a relationship between the derivative and the integral, and that relationship helped us find integrals quickly. Part two says this, basically, of the fundamental theorem, that the derivative and the integral are kind of opposite operations. Okay? So I'll do an example that utilizes this. So for example, the derivative of the integral from 0 to x of sine of t squared dt, okay, is basically this function evaluated at x. Okay? Just like here we have this function evaluated at x. Okay, so that's equal to sine of x squared. Period. I don't have to find the integral and then take the derivative. Okay? I know that the derivative cancels out this integral, which is a function itself. Okay, yes?
What's the whole point of it then? If you're just going to be left with that, what does it do?
Well, the point of it is trying to find a relationship between the derivative and the integral. Okay, the whole point is that they're opposite operations. Okay? All right, so let's write the result here. So what we just discovered is the fundamental theorem. Okay, and here's what it says. Let f be continuous on the closed interval AB, and let C be some number in AB. Okay? And then the function f defined by this kind of accumulation function, very similar to the one I did in this example. Is differentiable let's do some examples here.
Question.
Yeah.
So is the antiderivative and the integral just the same thing in a sense?
No, the antiderivative is a function.
But
The
when,
integral is a number.
but when you're solving the integral,
You're using an antiderivative, yeah. But there's a very important distinction between antiderivatives and the integrals. Okay? The integral is a number. Okay? An antiderivative is family of functions. Okay, and I haven't really said anything about antiderivatives yet. Okay? So let's find the derivative of this function. So, if this were just x, then it would be very easy. The answer would just be tangent of cosine x, right? Except this isn't x, this is a function of x, right? So, before I do this problem, I was hoping that my function would look like this. Yes? If this is what it looked like, then I could do the derivative very easily. Right? But that's not what I have. What I have is the derivative, not of f of x, of f of what? 2x. I have the derivative of f of 2x, right? And according to the chain rule, that's the derivative of f, leaving the inner part the same, times the derivative of the inner part, which is 2. Okay? Now, according to that theorem, I know what f prime is. F prime is just tangent of cosine x. Yes? But I want not f prime of x, I want f prime of 2x. Right? So that would be tangent of cosine 2x. And then we have times 2 over here. Okay? I'll do another one like this. So, let's find the derivative of the integral from 0 to x squared of ln t dt. Now I know we don't know anything about logarithms in this class per se, but just think of it as some function called ln. Anyhow, again, we're talking about a function from 0 to x. Actually, let's make this from 1 to x squared. Okay. So if f of x was the integral from 1 to x of ln t dt, then we'd be okay. All right. But we could write this question in terms of capital F. Capital F looks good. What we're looking for is the derivative of not f of x, but f of x squared. Again, with the chain rule, it's the derivative of f, leaving the inner part the same, times 2x. Very good. So then, f prime is just ln. Okay, f prime of x squared is ln x squared. Ln of squared times this 2x over here.
Usually, you know how you take the upper bound or whatever, and then you would subtract it from the lower one, like.
That's if I want to calculate the integral. I'm not trying to calculate the integral, I'm trying to calculate the derivative of the integral. Okay?
So how can you take that top one into consideration, or you plug it in and not the bottom?
The theorem tells me that it doesn't matter what this number is. Okay. So let me do this. Let me do this a long way. Okay. Let's find out what the derivative of 4t squared. Okay, let's figure this out. And we're going to do this manually, which means we're first going to do the integral, and then we're going to do the derivative. Okay? So let's do the integral. What's the integral of 4t squared dt? 4t cubed over 3. Right? And you want to evaluate that from 1 to x, right? Okay. So then that would be 4x cubed, 4 over 3x cubed minus 4 over 3. Yes?
Yes.
Okay. Now the derivative of this is 4x squared. The derivative of this is 0. Right? So the shortcut using the theorem tells me that to do the derivative of the integral, they kind of cross each other out, so to speak. And it's just plugging in up integral 4x squared. Okay. Except for this one, I could do this, but for this question, I couldn't even integrate the ln. I don't know how. Okay? As a matter of fact, something like tangent of cosine t, we can't even find an antiderivative for that. Okay? So we wouldn't have been able to integrate this in the sense of finding a function whose derivative of this is this. Okay? So okay. So for the fundamental theorem, we are talking about, we're requiring this function little f to be continuous. Now, last time I said that if this number exists, yes, then we say f doesn't have to be continuous for this to exist. F just has to be integrable, right? Yeah?
What does that mean?
It just means that this number exists. Now this number is based on a limit, right? Whenever we have expressions defined with limit, we have to be careful because the limit might not exist. Right? So this was defined as the limit of the partition norm going to 0 from sum. Yes? So if the limit doesn't exist, this number doesn't exist. So if the limit exists, we just say that this function is integrable. Now, for the fundamental theorem to work, we're requiring that f be continuous. Okay? So it's not enough that f is integrable, but it has to be continuous. So this is just a little housekeeping theorem, but it'll give us a wider picture of where does differentiability and integrability and continuity, how do they relate to one another? So this theorem basically says that if f is continuous, on AB, then f is integrable. On AB. Okay? So to put everything together, being differentiable implies being continuous. Okay? If you know that the function is differentiable, you know it's going to be continuous, right? And this tells me that if a function is continuous, then it's integrable. Okay. Let's think about this relationship for a second. So we're going to say that integrability is kind of the weakest condition. Okay? Because the opposite implication does not hold. Okay, so if the function is integrable, it doesn't have to be continuous. Right? For example, this function is actually integrable. Okay? So except we couldn't integrate this using the fundamental theorem, because the fundamental theorem requires that f be continuous. Okay? But it is integrable. In other words, if I set up the Riemann sum and try to take the limit, I will get an answer. The limit will exist. Yes? But I could not use the fundamental theorem to integrate a function that looks like this, because it's not continuous. Alright? So if you're differentiable, then you're definitely continuous and you're definitely integrable. Okay? If your function is integrable, it may or may not be continuous. It may or may not be differentiable. Okay? This function is not continuous and it's not differentiable, but it's integrable. Okay? So if you take all the functions in the world, the ones that are integrable are more than the continuous ones and the differentiable ones. Okay? The set of functions that is differentiable is very, very small compared to the set of functions that is integrable. Does that make sense? It requires so much more work to be differentiable than to be integrable. Right? Great. Okay. What is the mean value theorem? Who can remind us of what the mean value theorem says?
F times C is less than or equal to F of B and such variable.
Okay, so what is the word mean in mean value theorem means what?
Average.
Average. So that's the average value of what?
Function.
No. It's not the average value of the function. It's the average value of the derivative of the function. Okay? That's what the mean and mean value theorem says. It's the average value of the derivative function. Okay? Okay, let me remind you. I wrote this down. Okay, this quantity is the average rate of change. Right?
Mm-hmm.
This is the average rate of change. We're just saying that
At one point.
at some point the average rate of change equals the instantaneous rate of change. Yes? Does that make sense?
Yeah.
Okay, so that's the mean in the mean value theorem. So you can think of this as the mean rate of change. Yes? So that's the average, that's the quantity whose average we're trying to calculate. So if you want to calculate the average speed, right? There's two ways you could do it. You could take all the speeds and divide by however many speeds you got, right? That's how you calculate an average. Or you could just take the final position minus the initial position divided by how long it took to get there. So that's how you calculate the average speed. Okay? Under certain conditions of the mean value theorem, we're just saying that the speedometer will at some point show, okay, the average speed. Yes? All right, that's what the mean value theorem says. So it's about the average value of the derivative, of the rate of change of the function. Now, what if I want to calculate the average value of the function itself? How do you calculate an average of a group of numbers? Add them all and divide by however many you have. Okay. So I'm going to start with a function that's integrable on AB. I don't need it to be continuous. I'll take the weakest possible condition on f, which is integrability. Suppose that is integrable on AB. So f has so many values in AB. So if I give you a picture of that, right? So f has a value here, it has a different value next to it, has a different value next to it. So at different values of x from A to B, you have so many values of f. Yes? So my goal is to find a meaningful way to define how to calculate the average of f. Right? Now how many values of f do I have between A and B? I have so many, right? I have so many. So I couldn't possibly add them all because I would have to divide by infinity. Right? And I couldn't add them anyway. What could I? How do you add function values? That's how you add them. Right? This is a sum. You add all the values of f from A to B. Right? That's what this thing does. Right? You cut it up. You take an x, and you take the function value at that point. Plus, it's a sum, right? Exactly. And then you want to divide it by the size of your set. Okay. So we can't actually count how many numbers there are from A to B, but we can measure this set a little differently, right? We can measure the size of our set. And it's very easy to measure the size of A to B. You can just take the length of A to B as your measure for its size. Does that make sense? So I'm going to divide this by the length of A to B, which is B minus A. So I'm going to divide by B minus A. I can just write it like this. The average of f is 1 over B minus A times the integral from A to B of f of x dx. This is a definition. Okay? So if I want to calculate the average function value, I add them all. I divide by the length of the interval I'm adding. Does that make sense? So, and this makes sense. And you don't have to think about it, you don't have to write this down, but check this out. Let's say I want the average of f prime. Yes? The average of f prime. Yes? Okay. So if I have f prime, that means that f is differentiable. That's why I can write f prime. Yeah? So if f is differentiable, okay, then it's continuous, right? So if I use the fundamental theorem, if I assume that f prime is continuous, then find a function whose derivative is f prime. F, right? Okay, so I can do f at b minus f at a, right? Do you see that? So that's f of b minus f of a over b minus a is equal to average of the derivative. Does that make sense? So that's just like the mean value theorem for derivatives. Okay, that's the idea. Okay. But anyway, this is a product of b minus a, which is the length of the interval ab, and the average value of f. Well, if you take the average value of a set of numbers, then it has to be between the lowest and highest value, right? Okay. So the average value of f is some number between this and the highest point here. Right? That's the largest value of f, that's the smallest. So the average is some number here. Let's say this is it. This is the average value of f, right? What kind of picture can you draw to represent this quantity here? It's a rectangle. What's the base? And what's the height? that's the area. Actually, that's a really bad picture because that's not what the average value would be. You draw a better picture. Okay, so actually the average would be somewhere here. Okay. There we go. Okay. So what this is saying is that the area under this special rectangle is the same as the area under the curve. Okay? So the area under the curve would be all this, without this part, of course. So that's what we're saying, that the average value of f is a number so that the rectangle formed by the interval length and the height of the average value of f. So it's a rectangle whose area is the same as the area under the curve. Okay? So that's another interpretation of that. Now, does the function value ever take the average value?
Yes.
Yes.
What's the condition that's provided?
Continuous.
That f is continuous. Okay? Does that make sense? So according to this picture over here, yes, there is a point between a and b such that the function value is equal to the average value, right? But that's provided I have a continuous curve, right? If I happen to have some discontinuity here, then that wouldn't be true. Yes? Okay, what you just said is the mean value theorem for integrals. Okay? That's what you just said. So let's write it down. If f is continuous on AB, then there exists a number C within AB such that the function value at that special point is equal to the average function value. Okay? Or, another way to write it is like this. It's just a different way of writing it. Okay, so what we said earlier was that if f is integrable, then this number makes sense because the integral exists if f is integrable. And this number is interpreted to be an average of the function. Okay? Now, if in addition to being integrable, if the function is continuous, then there is a number between a and b where the function value is the average value. Okay? So that's what this mean value theorem for integrals is saying. All right? Is that pretty clear?
Yeah.
Okay. Let's take a break. Let's take 15 minutes. Done? So those properties are very important, and you have to be very familiar with them. Those properties, together with the fundamental theorem of calculus, the first part, okay, are going to help you calculate integrals quickly and efficiently. So, the fundamental theorem requires antiderivatives. Okay, so what is an antiderivative? An antiderivative is a function or a group of functions whose derivative is the original function. Okay, so an antiderivative is a function whose derivative is, so let's say it like this. An antiderivative of f is a function whose derivative is f. Okay? And notice here we're saying an antiderivative, not the antiderivative, because there are more than one. So for example, x squared is an antiderivative of 2x because the derivative of x squared is equal to 2x. Okay? X squared plus 1 is also an antiderivative of 2x because its derivative is 2x. So we have to write down some quick formulas for antiderivatives. Now, so from integration, I mean, we inherit the symbol, okay, to denote the antiderivative. X to the n. Okay? So the integral of x to the n. So, in other words, if I were to read this, I'd say the antiderivatives of x to the n dx. Okay? That's what this symbol means. And since antiderivatives are used in calculating integrals, we kind of inherit the same symbol. But there's a very big difference between this symbol and this symbol, for example. This equals a number. This is a family of functions, or a function. Okay? So this was defined, this was called the definite integral, and this type of expression is called an indefinite integral. So that's another name for it. Basically means antiderivative. So instead of using the word antiderivative every time, I'll just write this symbol without any limits of integration. Okay? It just means that we want to find antiderivatives. Now, so we want to come up with a quick way of finding an antiderivative of x to the n when n is an integer. Okay, and if you just do this with x, what's an antiderivative of x? X squared over 2, right? Plus c to represent all the functions whose derivative is x, right? And then if you look for the antiderivative of x squared, what is that? X cubed over 3. So in general, if n is an integer, how could you write this?
Next to the n plus one.
Next to the n plus 1 over n plus 1. But here we have to be a little careful. Okay? This only makes sense provided n is not -1. Right? So you could use, so this is like the power rule for integrals. Okay? You could only use it if, so this rule doesn't work for this type of, an antiderivative of 1 over x. We can't find it using this rule. This is x to the -1. Okay? Actually, this is a special function that we deal with in calculus 2. So we won't have to deal with that right now. Okay. How about this one? We need a function whose derivative is cosine x. Sin x. Okay. We want a function whose derivative is sin x. Okay, so if we put cosine x, the derivative of cosine x is negative sin x, right? So to offset that, we need a negative here. Right? So this table that I'm writing is basically the same table I wrote for derivatives, but backwards. So derivative of what is secant squared? Tangent x. Cosecant squared, negative cotangent x, right? Yes.
The derivative of, due to the derivative of secant squared x, we can't find it.
No. All right. The derivative of secant x tangent x. The derivative of what is secant x tangent x? Secant x. And cosecant x cotangent x. Alright. That pretty much wraps it up, yes? Okay. Now, these rules, together with the properties of integrals, will help us calculate indefinite integrals of a large family of functions. So we'll do some practice problems now, and we'll demonstrate how we use these properties. So let's calculate this. Well, so if I were to refer to this, if I were to look at the property 0.15, where it says the integral of a summary difference is the summary difference of the integrals. Okay, or you could just think of this in terms of derivatives, that the derivative of a summary difference is the summary difference of the derivative. So just working backwards, I could say that this is antiderivative of 2x squared minus antiderivative of x plus antiderivative of 1. Right? Okay. And then using the constant multiple rule, I can say this is just twice antiderivative of x squared dx. I could probably write this as a power. This is x to the power of what? 1/2. Okay. Now calculating antiderivatives is going to be very straightforward. Actually, you could do it directly, or you could use the rules there. So for this one, Extrude over
2/3.
3. How about this one? So you have to add 1 to this, right? 3 over 2.
3 over 2.
Divided by 3 over 2. And the derivative of what is 1? Plus c. So you can take care of all the functions. Whose derivative is that, right? So, so a couple of things here. Each of these have to have a constant of integration, which is this. But if you add them all up, then you just get another constant of integration. So it's not necessary to put different constants of integration. As a matter of fact, when we do problems like this in practice, I don't have to show that I'm breaking up the integral into separate integrals. I could just come up with the antiderivatives directly. So you can take the constant as a constant multiple. The antiderivative of x squared is x cubed over 3 minus, this is just x to the negative 1/3, right? So if you add 1 to it, you get 2/3 divided by 2/3. Minus antiderivative of sine x is negative cosine x, so you get plus cosine x here. Let's see. Okay. Perhaps a nicer way of writing this would be 4/3 x cubed minus 3/2 x 2/3 plus cosine x. Okay. So how do you check your work then? How do you check that you have the right answer? You have to take the derivative of this, and the answer should be the integrand, right? All right. So let's take another one. Integral of x plus 1 times x minus 3 dx. Okay. Do we have a product rule? We don't have one for integrals, right? So I don't know how to do this. However, if I were to multiply this out, then I can find antiderivatives easily. Right? This is just x cubed over 3 minus x squared minus 3x. Alright? So similarly, if I have a quotient I don't have a quotient rule for antiderivatives, but I can simplify this expression with 4x to the minus 3 minus 3x to the minus 5. And then now all I have to do is apply the power rule. So let's see. So we have to add 1 to this power and then divide by the resulting power. Constant times, again, add 1 to this power and divide by the resulting power. Okay, now we can simplify this. So this would be negative 2 over x squared plus 3 over 4 x to the 4. Right? So here's another one. Integral of sine x times cotangent of x dx. So how would I work this out? Well, this isn't part of my table. Okay? But that's okay. I can write this as sine x times cosine x over sine x. And then cosine x, and that's easy. Okay? So your integrand may not directly appear as something that looks like one of the things in your tables, but with some basic algebra, you could make it turn into pieces at least, each of which can be done using the rules that we have. Okay. So anyway, the whole point of calculating antiderivatives is to do definite integrals. Right? That's the whole point of it. That's why we came up with this, is so we could calculate definite integrals like this one. So integral from 0 to 1 of square root of x dx. Okay? So it's easy if I write this as a power. And the fundamental theorem says I just need to get one of the antiderivatives. I don't need to get all of them. Just one of them. Okay, so that would be 2/3 x to the 3/2. Right? And I don't have to put plus c because I could pick the simplest one. And I'd have to evaluate this from 0 to 1. Okay, so what that means is I can evaluate this function at the upper limit of integration and at the lower limit of integration, and I subtract the two. 2/3. Okay? The square root of x is a non-negative function. Right? So I just calculated the area under the curve of the square root of x from 0 to 1. Right? Remember how bad it was to do these things in the beginning? To calculate areas? So we got that.
Just for notation purposes, it should be 3/2, right? As the exponent. Is it 3/2?
Yeah, 3/2. Okay, sorry. Right. So the integral from -1 to 1 of x cubed dx. Okay, so take an antiderivative of x cubed. Okay. So that would be 1 to the 4th over 4 minus -1 to the 4 over 4. So that's a quarter minus a quarter, which is 0. Let's draw a picture and try to make sense of this. What type of function is x cubed?
Function.
Symmetric with respect to the origin.
Symmetric with respect to the origin. So, if I were to draw a picture that represents the integral from -1 to 1, that would be this area, which is negative, and this area, which is positive. And it's not hard to argue that these two areas are equal, right? But this one is negative because the function values are negative. And this one is positive because the function values are negative. But these two regions have the same area, so they would cross each other out. Okay? As a matter of fact, this is true for any odd function. Right? Any odd function over an interval that's symmetric, which means 0 is in the middle of that interval, would give you 0. Okay? cosine pi is the function evaluated at pi minus function evaluated at 0 is negative cosine 0. Okay? Now what is cosine pi? It's negative 1, right? Times negative is positive 1. Minus minus 1 is plus 1. So that's equal to 2. Right? Again, it's sometimes useful to kind of draw a picture and understand the geometry of what's going on. This is the graph of sine x from 0 to 2 pi. So this is the region that we just calculated. The area of this region is exactly 2. Yes? What do you think the area, what do you think the integral would be from 0 to 2 pi?
It's 0.
0, because this region is the same as this, right? But this one's negative. Okay. Very good. Okay, and then finally, let's compare this with this. Okay, so we want to do these two integrals and compare them. This was twice the integral from 0 to 1 of x squared dx. This is the integral from negative 1 of x squared dx. And then we're going to see why what we get makes sense geometrically. So if I do twice the integral from 0 to 1 of x squared dx, that's twice, now the integral, that's x cubed over 3 from 0 to 1. Right? So that's twice. So at 1 it's 1/3, minus at 0 it's 0/3, so it's just 0. So the answer is 2/3. Okay? And then if I do the other one, the integral from negative 1 to 1, then I get x cubed over 3 from negative 1 to 1. So at 1 it's 1/3, minus at negative 1 it's negative 1/3. What is that? 2/3, okay. So something special happens here geometrically. Let's draw a picture of the first expression over there calculates the area between 0 and 1 under x squared, and then multiplies it by 2. Okay? This expression over here, which is the same curve, right? It's supposed to be symmetric. Okay, it's the same curve. We're calculating the area from negative 1 to 1. So it's this area and this area. Yes? Together. And obviously, because it's symmetric, this region is the same as this region. So doing this and then multiplying by 2 is the same as doing the integral from negative 1 to 1. Do you see that? Okay. So this actually works with any even function, not only x squared. As long as you're symmetric with respect to the y-axis, then computationally this is easier to do than this, right? Because whenever you have to plug in 0, it's much easier than when you have to plug in numbers other than 0. Yeah? So if you notice that your function is even, and you notice that your interval is symmetric with respect to the origin, then just calculate half of the integral and multiply by 2. Does that make sense? Okay. So next time we'll make that into a theorem and we'll make it more formal. But for the rest of the lecture today, I want to answer questions from your test. this last test is kind of important, and the grades were all over the place. I mean, they range from 0 to 290, and 5 people got A, and like 5 people got B. So a lot of people did very well compared to the first few tests. But then there were some fundamental problems that I think that a lot of you didn't understand the question. So let's talk about that. Because a lot of the concepts that I'm going to ask you to do is going to be based on what we did in chapter 5 and what we did in chapter 4. The most interesting problems are problems that combine the two chapters together, 4 and 5. And you'll have, I think you already have 1 or 2 homework questions in this homework assignment that asks you to find the maximum of a function that's defined by an integral, right? So finding maximum and minimum is something we did in chapter 4, but if the function is defined using an integral, then you have to use some of the ideas we developed in this chapter. So let's answer some of the questions that you didn't do very well in the test. Yes?
Number 6.
What's the question?
Semicircle of radius r. You want the paper?
No. Keep reading.
Consider a semicircle of radius r whose diameter serves as the side of a triangle. What is the largest area of such a triangle if its third vertex is to be on the semicircle?
Okay. Semicircle of radius r, right? So we'll put this semicircle on an xy axis, where the center of the semicircle is at the origin. So this is r, negative r, and this is r. And these 2 points are the 2 points of the triangle, and the third point is on the semicircle, right? So let's say this is the third point, xy. So if that's what your third point is, then this is your triangle. Yes? Is that clear so far? So as this point moves, the rectangle, the triangle changes. So it changes area. For example, if the point were here, right? Then this is your triangle. And it's a very small area. Yes? So this has bigger area. This will have bigger area. So intuitively, without even doing any mathematics, you could probably guess that if the point was here, then you'd have the largest area. Because as soon as you cross that boundary, let's say you go back down here, this triangle has the same area as this triangle. Right? So all you have to worry about is this part. And you can probably guess that you get the largest possible triangle if that's the point. So I'm asking you to do this with calculus. So you have to define a function, an area function. Well, the area is half times the base times the height. Okay. So that's half. The base is always the diameter for all these triangles. Okay? Which is 2r. The height depends on where the point is, right? So if this is your point right here, the height is measured perpendicular to the base. This length is just y, right? The constraint is already built in. You don't have to write a separate equation for the constraint. And so a is actually just a function of y. R is fixed. So a of y is ry. The domain of this function, well, what's the smallest thing y could be? Well, the most extreme situation is if the point is here, in which case y is 0. And the most extreme situation, on the other hand, is if y is here. It's r. So this is the function that you have to maximize in this domain. Okay? Right. So you find the derivative, so you can find the critical numbers. When is the derivative equal to 0? Never, because r is not 0. R is just some fixed number. When does the derivative never exist? Well, it always exists. So in other words, there are no critical numbers. Okay? So then where do you look for the extrema? At the endpoints, right? Because the first thing we did in the first section of chapter 4, we said you find the critical numbers, you evaluate the critical numbers at the function at the critical numbers, and then the function at the endpoints. The largest is the largest, the smallest is the smallest. So all I have to do now is evaluate A at the left endpoint and at the right endpoint. A of 0 is 0. A of r is r squared. Obviously, this is larger than 0. Right? So this is your maximum. That's the maximum area. And then it'll only happen if the y-coordinate is r. In other words, only happen if this is the point. That's the triangle with the largest possible area. Okay, that's all. That was, a lot of people missed that, but that was one of the easiest problems of the test. And I think you overcomplicated it, a lot of you. You started writing the equation of the circle, x squared, y squared equal r squared, and you got really fancy, and you didn't get anywhere. Yes?
Is it possible to solve that way?
Yes. Yes.
In short.
No. There are a lot of other ways to solve this. I mean, you could solve this purely geometrically. There's a theorem in geometry that says that these two chords always make a 90-degree angle if they touch the diameter endpoints, right? So another way to calculate the area of a rectangle of this is to come up with a formula that's based on the product of these two. Because if these two are right angles, then the area of this is half of this times this. Yes? Okay, so you could come up with this length, and you could come up with this length. And you realize that the only way that you'll have the largest possible triangle is if these two lengths are the same. And these two lengths will be the same. In other words, you have an isosceles triangle only if the point is here. That would make an isosceles triangle. And that's another way to solve it. And there's many, many ways to solve it. This, I think, is the simplest. So I wouldn't even talk about the other methods. I think somebody did this direct triangle business, and they got it right. God bless you. Is anybody here that did that with right triangle? You get r square root of 2. Maybe I'm just dreaming these things. I swear I saw it.
Yeah, I did that.
You did do it that way.
I did it, but I didn't do the way I did it exactly how you did it. My triangle was at the top.
Oh, okay. Now above the but you got it right? You got full points for that one? Yeah. Okay, so you were the one. Thank you for the geometry. It's always nice to see geometry. Okay, other questions? Well, you guys look like you all got hundreds.
What about the Newton's method?
Oh, the Newton's method one. Oh God, what did that look like? Basically, you have to say that it doesn't work because the tangent lines change slopes from positive slope to negative slope. Because there's a local min. I think this was the picture, and this was the guess. You're supposed to draw a picture. The picture looks like this. Okay? So what happens is these guesses jump back and forth. Okay, and I think there was a root here. This is the one we're trying to find. And Newton's method just keeps, just jumping back and forth here. It never gets close to this. So you're supposed to say that no, it doesn't converge. The reason it doesn't converge is because there's a local min that separates your first guess from the actual answer. You said something like that and you got full points. And you had a good picture.
If we were to do that for long enough, would it eventually get somewhere where, like near the point of that? No.
It wouldn't. I mean, if you start here, you jump here, that's fine. But as soon as you jump back here, what's going to end up happening, this is going to converge to the wrong value. This might converge to this value, which isn't the answer. The answer needs to converge to the root. That's what it claims to be. So the moral of the story is, if this method is beautiful, your initial guess can't be too far from the actual answer. That's the idea. And I was testing your knowledge of the geometry of Newton's method, so you can draw the picture. Other questions? Okay, this was your only chance to ask questions about this test. Yes?
With A part B, you would just have to do long division.
Yeah, if you do long division, then you get, the derivatives are really simple. Derivatives are actually 1 or 2 lines, and you get the answer. And I think I did something like that in class.
Is that a common trick with a lot of? Does that work often?
Yeah, if the numerator has a larger degree than the denominator, then you want to do long division.
Okay.
Because you get simpler things. Yeah.
Number 11.
Okay, what does it say?
X, y, and z are positive numbers. Prove that x squared plus 1 times y squared plus 1 and z squared plus 1 over x, y, z is greater than or equal to 8.
All right. We don't need that much room. So x, y, z are positive, not zero, positive numbers. We have to prove that x squared plus 1 times y squared plus 1 times z squared plus 1 over x, y, z is at most, is it greater or equal to 8?
Yeah.
Greater.
Okay. So, and I told you, in order to prove this, prove that this function has a minimum of 2. Right? I told you to prove that this function has a minimum of 2. Okay? So that's what you have to start by. Following the hint, the domain being greater than 0. So prove that this is, okay. So again, following that what I just said, I'm going to rewrite this function as x plus 1 over x. Okay? And then I'll do the derivative. So 1 minus 1 over x squared. And then if I rewrite this, then I get x squared minus 1 over x squared. And my critical number, I just have one critical number, and that's x equal to 1. Because remember, my domain is x greater than 0. So neither 0 nor negative 1 is a critical number. The only critical number is 1. Okay? All right. So if I were to do so here's 0, here's infinity, here's 1. And if I were to look at f prime, if I take an f prime between 0 and 1, if I take an x value between 0 and 1, then this would be negative. Okay? If I take a test value after 1, this would be positive. So what's happening is this function is decreasing and then increasing, right? So this is a local minimum, but it's also the absolute minimum. Okay? That's the lowest it can be ever. So there's an absolute min at x equals 1. To figure out what the value of that min is, I plug that in into the original function. X squared plus 1 over x, so 1 plus 1 over 1, which is 2. That's the absolute min. That means that f of x is greater or equal to 2 for all x greater than 0. Right? Does that make sense? Yeah. That means f of, this is the trick, f of y is greater or equal to 2 for every y greater than 0. Right? Does that make sense? It means f of z greater than or equal to 2 for every z greater than 0. Yes? That means f of x times f of y times f of z is greater than or equal to 8. 2 times 2 times 2. Right? Okay, f of x is x squared plus 1 over x. F of y is y squared plus 1 over y. F of z is z squared plus 1 over z. Greater than or equal to 8. This is what you have to prove. Okay? That's the trick. Does that make sense? Okay. So what you do for number, I guess the last one is very similar to this, right? I say look at the hint of the previous problem. So what that means is, for this one, I gave you the function, and I was hoping that you realize that this is the same function as this, is the same function as this. If each one is greater than 2, then the product is greater than 8. Okay? That's what I was hoping that you'd see. And some of you saw it and did it correctly. But I gave you this function. So for the next one, I don't remember what the problem is, but you have to come up with another function like that. Yeah? So you just use one of the variables, come up with a function, show that that function is less than or equal to 4. Yes? Then the product of that function by itself is less than or equal to 16. And the way you find the domain is that rectangle means x is between negative 2 and 2, y is between negative 2 and 2. So your domain, if it's only f of x, is between negative 2 and 2. Okay, that's how you use the picture. So you should try it. If you still don't get it, then I'll solve it next time. Try 12. Okay. To come up with f of x, just use the x terms in the product. And this time you're trying to find absolute max. Okay? Within negative 2, 2. Okay? Within that negative 2, 2. Okay, that's it.